Okay guys, we need to finish up this handout here. A lot of this is reviewed. There will be a little bit of new stuff, again, in the context of organic chemistry, particularly reaction coordinate diagrams. Also calculations. How are we doing on these here? And then we had a test in between. I probably want to address some of this during a little bit of lab lecture. Okay. There's also a calculation to do over here, actually two with the fluorine and then doing it with the iodine. Okay, usually working on those. But let's move on to kinetics. Kinetics describes the rate of the reaction. Okay, thermodynamics, you're looking at stability of starting versus end. It has nothing really to do with rate of a reaction. Rate of the reaction, we want to mainly look at something like activation energy. Again, a lot of this concept should be reviewed. We'll look at some particulars. Reaction coordinate diagrams. Okay, you'll be asked to draw these because they sort of illustrate the reaction in terms of energy and relative comparison of, for example, energy of reactants versus products. We have a progress of the reaction just in terms of going from here to there, the progress, because it's not just instantaneous in terms of energy, and then some type of energy plotted here. Reactants, there's no actual numbers here, it's sort of just relative, okay? We have, as the reaction proceeds, an actual increase in energy of the system up to a point, and then we fall down. Comparing here to here, we have a negative delta G. The reaction is exothermic. The system has lost energy. But this here is our activation energy. Right? Energy of activation. What's also going on right here? For example, this high energy peak here. What is the name of that? What is that? Is it reactants? Is it products? What do we maybe call that? Can we give it any name?
Equilibrium.
Transition state, right? And that's sort of the maximum energy of the transition state there. I mean, all along here is transition, but it kind of peaks out here, yeah? And that's the highest energy. Transition state would be where the bond is like maybe being formed and broken. There's this intermediacy. This reaction coordinate diagram over here shows an endothermic reaction. Again, one transition state leading to products. And there's some variety of stuff here that's just for you to look at. I'm not going to read it to you, but it should make sense. Mainly review. Reaction coordinate diagrams down here. We have four. Which reaction is most favorable? What does it mean to be favorable? That's sort of a term that's maybe in quotations to me. Favorable would be really looking for an exothermic reaction. Which reaction is most favorable? It's hard to tell, but these two are both exothermic, but this one looks like it's a little bit more exothermic. Yeah, it's pretty close, but if you get out a ruler or something, looks like the B is sort of the most exothermic and thus most favorable. Which favorable reaction is fastest, though? Which ones are favorable? The top two, because they're exothermic. Favorable. Which of the top two is going to be fastest? A. But it's not most exothermic. Because we're talking about rate. Rate doesn't depend on this. Rate depends on the energy that's needed to do the reaction, the activation energy. Less energy needed to do this, more energy to do this here, more activation energy required. It's going to be faster reaction. Because for example, at a given temperature of maybe room temperature, 22 degrees, that amount of heat is able to get more of these molecules over this than this. So activation energy is what controls the rate. All four of those reactions only have one transition state. There's no intermediate. A transition state is not an intermediate. When we talk about intermediates, we're talking about a discrete intermediate that we can show a traditional standard Lewis structure for. Transition state is going to be partial bonds and all this sort of vagueness. Reaction coordinate diagram down here does show an intermediate. One intermediate. We have an alkene reaction, type of reaction we'll be looking at in just a little bit. Transition state leading to an intermediate. The intermediate is going to be in an energy well. Because the transition state leading to it, the transition state is going to be higher. Where the bond is forming and bond is breaking. All this magic is going on. That's actually high energy. But then it settles into some kind of a product. But it's an intermediate product. Now, intermediates are typically not isolated. They occur along the reaction pathway. Okay? Not isolated. Usually. Now, maybe there's some... I told you everything's got an exception, right? I ain't going to explain the exception, but this is the opening statement, not isolated. Then we have a transition state. This is really two reactions in one. We call this two elementary steps within an entire mechanism. But each elementary step has a transition state. Then we have a next step, let's call it a step, with a transition state leading to actually the final product. Because at that point, everything's done. So understanding reaction coordinate diagrams. And if you have questions, please shout them out. What's over on the left there? Very important, rate determining step. Which step of this reaction is rate determining? It's going to be a rate determining. The overall rate depends on which step?
Step 1.
Why step 1?
Because it has the highest activation energy.
Yeah, it has the highest activation energy. Step 1. Really, it's which step is more difficult? Step 1 is more difficult. It requires so much more activation energy than this. So step 1 is the rate determining step. RDS, rate determining step. That is, when you go to the SAS cafeteria, what's the rate determining step? You moving through the line and choosing your food, or you choosing the table, which is usually the rate determining step.
Food.
Usually moving through the line, because there's a line there, everybody's taking their time to choose. Okay. If you want to say, hey, next time I go to SS, I want to do it faster, would you say, hey, yeah, let's make sure after we get our food, we run to our table? I mean, well, in the scenario, you might say that it's overall faster, but really you need to focus on getting through the line faster. Now, I can see an argument for my scenario didn't work out. You guys getting out of this door, what's going to be the rate determining step? All of you getting there or moving through the door? I think maybe moving through the door, because you got to go through one at a time. So a lot of you may not even rush over there, because you know you're going to get over there and have to wait. That's the rate determining step. That is, the second step is actually fast. Why is this faster? Because it doesn't have much activation energy. It's easier to get over this hill. Why is this activation energy fairly low? Why doesn't it come up like this? Well, that's sort of a standard here. We would not expect it to be high. Why do we expect this to be kind of low and not go up high? Sort of on the next page, but I'll go ahead. The reason we expect this to be low is because we're falling downhill. It should not take much energy to fall downhill. And that's usually just an assumption we sort of go with. That's usually our starting point. Are there exceptions? Yes. Doesn't take much energy to fall downhill. If you want to try this, go to the third floor up here on the steps. Stand at the top of the steps. Stand up there. Okay? It's not going to take much energy, but just kind of bend your knees a little bit and sort of do like that. You're going to fall downhill. It doesn't take much effort to fall downhill. Now, on the other hand, you go to the bottom of the steps and you do this. You ain't going anywhere because it takes much more energy to go uphill. Right? All right? What else can we talk about? We'll look at which way the reaction is going to go if it has two different routes. This reaction here, a very standard alkene reaction. Alkene with like HBr. We'll go two different pathways. One pathway leads to this. One pathway leads to that. Two intermediates. This one is higher energy. By the way, these are the two intermediates. They're both cations. Why is this carbocation higher energy than this one? Well, how do you stabilize a positive? This has more donation. Inductive donation. This only has one sort of chain donating, which is going to be a better cation. One that has three rich friends donating electrons. It's more stable. Thus, if we plotted it in terms of energy, it would be lower in energy. This reaction can go to, you have a choice. Which one's going to be preferred? The lower one. But why? It's not so much this, it's really that. Because as the energy, the reaction is taking place, I can give it an out. Water running downhill. Well, just running down the road. You ever see water rolling down the road after it rains? Okay. And it comes here, and then there's a road that goes downhill, and there's a road that goes up. Which way is the water going to go?
Down.
It's going to go downhill. Okay? Energy flows downhill. Same thing here. This is energy. Which way is it going to go? I've got a choice. Boom. I go lower. Takes the lower energy pathway. That's why it forms this. Not so much this. Now, does it make sense that this should have the lower activation energy? Yes. Because a more stable species is going to be easier to form. That's really what we said on the previous page, but now we just have two things. A high energy species typically going to have a high activation energy leading to it. Lower energy, lower transition state energy. This is really why the reaction comes this way. The water flows downhill. Okay? So, again, understanding your reaction coordinate diagrams, and we'll be talking about that same exact reaction in a little bit, and we'll show these two intermediates, and I'll try to explain why this one's favored. But really, we already did that right there. One down here. Now this one is a little bit, goes against something we said, more of an exception. We'll actually be looking at the same reaction coordinate diagram here in test 3. Reaction of a diene, two alkenes, reaction with HBr. It actually gives a common intermediate, so there's no choice here. The choice actually comes in the second step. By the way, even when you go, this is one step here, yeah? 2 steps. Of the 2 steps, which was rate determining?
First.
Yes, this is a rate determining step. What do we want to call the second step then? Typically we call it what? Not rate determining? Fast, okay? Compared to the slow rate determining step. The slow step is your rate determining step. So this is just standard terminology. Rate determining step and then the fast step. There's 2 different possible fast steps. 2 different outcomes, a 1,4 product and a so-called 1,2 product. Which one's more stable? 1,4 product, right? But which one's formed easier? And thus faster, because easier is going to be faster.
1, 2.
The 1, 2 product.
Yes. Here we go. I have a choice. I'm going this way. But that leads to, see, this is sort of an exception. Usually, the lower energy intermediate or product usually has a lower transition state energy. But that's not the case here. So this is an exception to our original kind of statement. So we'll have to understand why this is. Why is it actually slower to form the more stable? Okay? We'll have to discuss that. With the questions on the side. By the way, the idea that the transition state sort of mimics the product, that's called the Hammond postulate, but why is the 1,4 product more stable? Apparently we should be able to answer that if I ask it. Actually, I think we should be able to answer that. Why is the 1,4 product more stable? Why is this product more stable than this?
Lower in energy.
Somebody say lower energy.
Is that
Why is the 1,4 product lower in energy than the 1,2 product?
Because the bromine is a third bond on the CH2.
It's attached to what?
So the CH2 has a third bond. So it's
As a third bond?
the C has 2 H's. To get more stable, it needs 1 more.
Okay.
distribution?
My first difficulty is I can't quite hear you. And then I'm not quite following you while you're saying it has more bonds or H's. I'm not quite getting you. Well, they're both alkenes. Now see, this is sort of a linear formula. It's not fully Lewis structure, it's sort of partially condensed, yeah? You gotta really know what's going on here. This alkene has 1 carbon substituent. This alkene has 2 carbon substituents, which is going to be more stable.
2.
2. Remember last time I actually told you how you would forget it. Don't forget it, they're already applying it. Okay? It's got 2 carbon substituents. That's the answer. Carbon substituents. Because how else have we judged alkene stability thus far? Think about it, guys. Last time we talked about alkenes, ways to judge alkene stability. Today we're asked which alkene is more stable. So you just go back and say, apply the information. So you got to understand what we've covered and why, and then what type of questions would be asked. If you don't go back and think, then it's like you don't even remember what we did last time. And obviously that's not good. So every time we cover a topic, then anticipate, well, what type of question would come from this discussion. What can we say down here? This is a good old SN2 reaction. We'll cover it during test 3. There's no intermediate. There's no intermediate here, right? That's just one transition state leading to that. If that's the end, there's no intermediate in the whole reaction. How can we make this reaction faster? Here's one reaction. How do we make it faster? Now, it's a kind of a loaded question because to what detail am I looking? Here's the answer. Yeah, what does a catalyst do?
Lowers the activation.
There's your answer. What?
Lowers the activation.
Yeah, we make this faster by lowering this activation energy down. There it is there, okay? But what if we were able to lower it down and make it like that? Then it would be faster. Now you also have to realize that if it said that, I could not have said, no, I really wanted you to tell me to stir it faster. That does not invalidate your answer. Your answer was correct. Maybe you didn't read my mind and know what I really wanted, but that doesn't mean your answer is not correct. So don't be afraid to give what you believe is a correct answer and then say, well, we were thinking about different things. Because the most simple is lower the activation energy. Well, then you could say, well, how would you do that? Some type of catalyst. Or maybe we change these, but then we're kind of changing the reaction. Okay, so in the end, being able to work with reaction coordinate diagrams and the various things that you see there in the terminology, and being able to ultimately draw them when asked to describe your reaction. Now, does that look similar to stuff you've seen in previous chemistry classes? Hopefully so, just more in the context of some specifics for me and for organic chemistry. Okay, we have a yellow. Intro to alkenes, I think we're done. You're watching nomenclature video. Any questions there? EZ terminology, very important. We'll look at more of the thermodynamic calculations in the lab. Okay, guys. So at this point, I'm thinking to me that the intro to the course is there. We're now really ready to move on into sort of a different chapter in our journey here. And that is chemical or reactions. Functional group transformations. Reactions of alkenes, turning an alkene into maybe an alcohol or an alkyl halide. So really we're kind of bumping it up a notch. We'll start more and more using the material that we've been looking at the past few weeks. Okay? We have a yellow outline. Everybody got one? They were passed out in the lab, I believe you. And they gave it out today, edition of HX. Of course, you have the outline in the syllabus, so you knew this was coming. 2 weeks ago, 3 weeks ago, you knew these topics were coming. What do you need? Would y'all pass that back, please? I'm going to send the whole stack. We'll start over here. Just pass it around, please. For example, the daily outline says stereochemistry is coming in about a week and a half, 2 weeks. So if you want to start reading that chapter, okay. So our outline. Now these questions here, these warm-up questions are the most basic that you'll see on a warm-up for me. These are introductory basics. Okay? Just the basics. These are examples of alkene reactions. Okay? All alkenes reacting. Our lab this week is an alkene reaction. Okay? A hydration reaction. I'll say more about this. Kind of want to get started doing stuff on the board. Very important will be mechanisms. This here is a newer handout page for me. I've had it for about 1 or 2 semesters now because I just have seen a need for it. I think it's very useful, or I would never have given it to you. Please read. We've got to really understand mechanisms. There's also some text about mechanisms, type page, some examples of how, what not to do. Okay, incorrect mechanism movement. All right. I included the acid-base mechanism question on test 1, at the bottom of like the 3rd page. Okay, it's very basic. Lone pair takes the H, the electrons move on to the atom. Okay, mechanism shows movement of electrons, not movement of atoms. So please start to read this and form questions and start thinking about your mechanisms. We'll certainly be doing that here in class. Many textbooks really don't talk about how to do mechanisms so much. Most of the books just sort of jump in it and start doing mechanisms. I think it's important to really understand what a mechanism is about. Okay, here's a summary of the reactions. Alkene reactions. When I give summaries like this, I try to give organization that is hopefully useful. And you should make note of the organization. For example, Roman numeral 1, these reactions involve what as the electrophile?
Hydrogen.
H plus. Okay? And I think that's a hugely important thing to recognize before you start just looking at what's going on. So if I could put some of these headings in neon lights, I would. Hey, this is important. A lot of times I just see students who, you got these detailed questions, but you really haven't looked at what's the overall goal here. What are we doing overall? Down below are other reactions. Okay? A good number. This may look daunting here at the beginning. What we need to look for is consistencies. If you find the consistencies, it will make it much easier. That is, you can't memorize 10 different types of reactions. If you learn the consistencies, it can become really just one type of reaction with just 10 different variables. So I encourage you to look for consistencies. So that's the summary page. We'll review back to it. The first reaction we'll look at is at the very top. That is reaction of an alkene. This happens to be a ring with HX. And what type of compound will that give? Alkyl halide. Then there's our outline. So, like I just said, addition of HX to give alkyl halides. Here's our key points we want to make sure we cover. And then we can move to the white handout from today. So the two will kind of go hand in hand. Outline versus sort of stuff that might be written on the board. Boom, I just wrote it on the board. So ready? Let's get going with the few minutes we have left. First reaction is addition of HX to alkenes, also known as hydrohalogenation. Hydrogen, halogen, that's what we're adding. Okay? First off, all these reactions are addition reactions. Well, if you look back over at the summary table, I bet addition is at the very top. Electrophilic addition reactions. It said that. And when you read it, you should think about addition. What does that mean? As opposed to just reading it and then reading the next sentence. Because these new words are very important. These are all addition reactions. That is, HBr is adding to this. very simplistically in that point. That is, this formula is this. The formula now has HBr added to it. It's an addition reaction. How does this reaction take place? That is, what is the mechanism? Mechanism is shown here. Okay, we know HBr is polarized. The H is partial positive, even if we keep it covalent. Now later on, we may, it's okay to just show it ionic. Because HBr it can actually be either. And in some cases, a reactant can only be covalent. But we should be able to work it either way. In both cases, the H is electron poor. Full plus or partial plus. Something that's electron poor, we're going to call electrophilic. Because if it's electron poor, that means it likes electrons. Like, I would like electrons. I'm electron poor. Like a poor person likes money. I need money. Okay? So electrophilic, a term that you need to make sure you know. Either way. The alkene is considered nucleophilic. The alkene has electrons. And a nucleophile, what is a nucleophile like? Like a nucleus. What is a winophile like? Wine. Okay, nucleophile likes a nucleus. Well, the important part there is the nucleus is positively charged. So really a nucleophile likes positive charges. That's what you have to get from that. So, is there a positive charge around? Yes, the H+, which is the electrophile. So that's how we have to assess with some terminology. Okay, the first step is the pi bond is a source of really a lone pair because the two electrons in the pi bond are not held tightly. And typical convention is to show the two electrons, sort of, instead of bonding, the two electrons are going to move and go bond to the H, okay, make bond to H, and these two electrons move on to bromine, which bromine wants electrons, it's trying to pull them anyway. Another way to show this is just show it from the, already have this ionized, okay? Now when these electrons come over and make bond to H, that's going to leave this carbon without a bond, or missing a bond. But this electron movement leads to this, and this is an intermediate. And a lot of times I'll highlight what bond we just made. And this is a carbocation. We call it a carbon cation. We call these a carbocation intermediate. That's the first step, intermediate. The second step of this mechanism is then the bromide, these electrons, then go and attack the plus. The negative attacks the plus. Bond formation. These electrons are moving to make bond here. I'm not saying that the lone pair just leaves the bromine and becomes a lone pair here. I'm not saying that. We're never going to do that. This arrow is indicating that this is making a bond. Just like when we did acid-base, right, and we had maybe an amine, and that one's, right, and we had like HBr, and we said these electrons go make bond to H. Well, these electrons go make bond to carbon. But it's not kicking anything off here. Of course, the two different ways were discussed on the previous pages. Two-step mechanism. Arrow shows movement of electrons. Now, atoms, okay, these are nodes. H+, Br- is acting as a nucleophile here. Two-step mechanism. Let's show a reaction coordinate diagram. Okay, let's call this maybe A, carbocation B. I'm not tall enough for the final product C, yeah? What do we have here? Reaction progress, some type of energy. Doesn't need to be overly detailed. This would be enough. We start with A, some arbitrary level. Now we can get more particular. Where do we want to put B compared to A? Higher. Why higher? Because it's charged. Okay? The carbon doesn't have an octet. It's charged. It's a higher energy species. We can put B sort of up here. Okay? And where do we want to put C, the final product? Lower. How compared to A, though? Which is more thermodynamically stable, starting or product? This is really calculations. Bond strengths, you can get that answer from calculations. We can't just sort of eyeball it and maybe make a good guess. Yes, what type of bond was broken? If you want to do calculation, what was broken in the starting material?
Ionic.
It's a double bond, in particular the pi bond was broken. What was formed in the product? A sigma bond to bromine and a sigma bond to H. We went from a weak pi bond to two stronger sigma bonds. Sigma bonds are stronger. We made stronger bonds. Is stronger bonds lower energy or higher energy? Stronger bonds are lower energy. Product is lower energy. Again, you can do calculations and use your bond strings. C would be more like down here. I'm going to put it too much lower, but it is lower compared to this. That is, this reaction should be exothermic.
Can you use an entropy argument to determine that as well, or only look at bond strength?
I kind of glossed over this. I'm usually going to plot just delta H. When you bring in entropy, now you're combining it and you're really looking at delta G. But if you want to talk about entropy, is this reaction's favored thermodynamically. It's exothermic, right? We just went through. Is this reaction favored by entropy?
No.
No, why not?
It's becoming more ordered.
Becoming more ordered. Why? Because two molecules are reacting to form one. So it's not favored by entropy. So the question is delta G overall favored? I don't know. So we're really looking at just delta H here. Okay, so how do we do this? Do we just do arrow, boom, boom? Or do we know there's a transition state? Yeah? Now from here, there's your energy well. Now that's the energy for the first step. Now we got to have some energy to complete the second step, which is what? Addition of the bromide to the carbocation. Okay, how much transition state do we need, energy? Not much, because we're falling downhill, remember? Doesn't take much energy to fall downhill. So just a wee little bit and boom. Just enough to give that bromide some energy to make it over there and make the bond. And then everything's going to be like, right? Which is the rate determining step?
First one.
Rate determining step. And this will just be fast. So, what is the name of the rate determining step, or what's going on in the rate determining step? Attack of the acidic H and formation of what? Carbocation intermediate. Yes, formation of carbocation is the rate determining step. Addition of the bromide is the fast step. If you want to make this reaction faster, which step do you want to focus on? Rate determining step. Forget about the fast step. That's not going to help you make it faster. Congratulations, you just made the fast step even faster. So what? The overall rate's still the same because it's controlled by the rate determining step. Okay, guys, we'll continue on. Please be looking ahead. Reading in your chapter, in your textbook. Okay? How does your textbook present alkene reactions? Have a good day, guys. See some of you tomorrow afternoon.